Hello everyone, welcome to the video lecture on interference of light. I am M. Satyavani, lecturer in physics, TNR College, Bhimavaram. Today I will discuss about interference of light in this lesson. First of all, I want to discuss about superposition principle. In previous classes, we have studied about superposition principle or principle of according to principle of superposition, when two or more waves when they in a medium superimpose each other, the resultant displacement of the wave is equal to sum of the displacements of the waves in the absence of others. For example, if there are two waves in a medium whose displacements are y1 and y2, the displacement of the resultant wave when these two superimpose each other is y, then y is equal to y1 plus y2. That is known as superposition principle. In superposition, if two or more waves so having same amplitude and wavelength, having constant phase difference, when they superimpose each other, the distribution of energy is no longer uniform. That phenomenon is known as interference of light. When a single source of light is present in a medium, the energy around the source distribution around the source is uniform. But if there are two adjacent exactly equal in frequency, wavelength and having a constant phase difference, that is, they are known as coherent sources, then the distribution of energy is no longer uniform. In the medium, at some places the energy is maximum, then we get a maximum intensity, we get brightness, and at some other places it is minimum, we get dark. This modification in the distribution of intensity in the region of superposition of two or more waves from coherent sources is called interference. Is called as interference. The phenomenon of interference was first demonstrated by Thomas Young. Phenomenon of interference was this phenomenon was first observed by Thomas Young, demonstrated by experimentally. And in this topic, I will discuss about what is interference, how the bands are formed, and what are the conditions for interference. That is, what are the conditions for good observation of fringes and fringe width, good contrast, etc. And also I will discuss about different types of interference. These topics now I will discuss in this lesson. First of all, interference, demonstration of interference by Thomas Young. We have already stated that interference is nothing but it is the modification or redistribution of intensity in the region of superposition of two waves from two coherent sources is known as interference. In Young's experiment, he allowed sunlight through a narrow pinhole S. This is the experimental figure for the Young's experiment, and S is a narrow pinhole. There are two more holes which are in front of S, and they are equidistant from S. They are very close to S. Sunlight is allowed to this pinhole, then according to Huygens principle, each point on the wavefront is a source of secondary disturbance. It moves in the forward direction. When this wavefront touches S1 and S2, it is divided into two wavefronts. It is divided into two wavefronts, and these two wavefronts superimpose each other on one another, and for dark and bright fringes are observed on the screen. These fringes are known as interference fringes or interference bands. Next, explanation on the basis of wave theory. How these fringes are formed, why some points are bright and some points are dark. This is explained on the basis of Huygens wave theory. In this figure, S1 and S2 are two sources of light. Light waves are, we know that light waves are transverse waves. Each wave is characterized by alternate crests and troughs. When crest of one wave falls on the crest of another, or trough of one wave falls on the trough of another, they mutually reinforce each other and the amplitude increases. Hence, intensity which is proportional to square of the amplitude is also maximum. Then at that point, maximum brightness is produced and a bright band is produced. This is known as constructive interference. Therefore, constructive interference takes place when two crests superimpose each other or trough of one wave falls on the trough of another. Next, for example, if a crest of one wave falls on the trough of another or trough of one wave falls on the crest of another, they are in opposite direction, so they mutually destroy each other. So minimum brightness is produced. Then we observe darkness at that point. This is known as destructive interference. In this way, alternate bright and dark bands are observed on the screen. These two phenomena, constructive interference and destructive interference, together are known as interference. This is explanation according to Huygens wave theory. In the figure, alternate bright and dark bands are produced on the or formed on the screen. The distance between any two consecutive bright or dark fringes is known as fringe width. Next, theory of interference fringes. In Young's experiment, he observed number of alternate bright and dark fringes on the screen. In this case, S1 and S2 are two coherent sources separated by distance 2d. The first condition for the production of interference, for the formation of interference fringes, is the two sources must be coherent. We cannot produce coherent sources from two individual sources. Therefore, a single wavefront is divided into two wavefronts and they are allowed to pass through S1 and S2. In this way, the two pinholes S1 and S2 act as two coherent sources. These two coherent sources are very nearer to each other. The distance between the two coherent sources is 2 small d. Then a screen is placed in front of the two pinholes, which is at a distance capital D from the sources. C is the point which is equidistant from S1 on the screen, which is equidistant from S1 and S2. Therefore, the path difference between the waves coming from S1 and S2, that is S1c and S2c, the path difference S2c minus S1c is equal to 0, as C is equidistant from S1 and S2. Thus, the point C has path difference of 0 corresponds to maximum intensity, the condition for maximum intensity. Therefore, the point C has maximum intensity and a bright band is formed at the point C. Consider a point P, any point P at a distance x from the center C. The waves reaching the point P from S1 and S2, virtual sources, coherent sources S1 and S2 are as shown in the figure. The path difference between the waves coming from S1 and S2 is, when they reach the point P, the distance travelled by the ray from S1 is S1p and from S2 is S2p. Therefore, the path difference is S2p minus S1p. The path difference between the two waves from the sources S1 and S2 is S2p minus S1p, that is equal to x into 2d by capital D. If you simplify the values of S2p and S1p, then we get S2p minus S1p is equal to x 2d by D. By solving the mathematical equations, we get S2p minus S1p is equal to x into 2d by capital D. We know that the relation between the path difference and phase difference is equal to 2 pi by lambda into path difference. Phase difference delta is equal to 2 pi by lambda into path difference x into 2d by d. That is the phase difference. Next I will discuss about intensity on the different points on the screen. And first of all, I derive the condition for the formation of bright fringe on the screen. Next, for the condition for dark fringe. First one, condition for bright fringe. The point P is bright when the path difference is equal to integral multiples of lambda. In superposition principle, in previous classes, when two waves having same frequency and constant phase difference, when they superimpose each other, the maximum intensity is produced when path difference is equal to n lambda or phase difference of 2n pi. Therefore, path difference in this case is for nth fringe. If nth fringe is formed at a distance xn from the center, then xn into 2d by d is equal to n lambda, or xn is equal to n lambda capital D by 2d, where n is equal to 0, 1, 2, 3 and so on. Lambda is wavelength of monochromatic light used, and d is the distance of screen from the source, and 2d is the distance between two coherent sources. The distance between any two consecutive bright fringes, any two, for example 1 and 2, 3 and 4, etc., n and n minus 1, we can calculate the value of distance between any two consecutive bright fringes. X2 minus x1, for example, if you take first and second fringes, consecutive fringes, x2, for substituting the value of n is equal to 2 in the above equation, x2 is equal to 2 lambda d by 2 small d. Similarly, x1, x2 minus x1 is equal to lambda capital D by 2d. If we calculate any value, x4 minus x3 or x7 minus x6, etc., we get lambda capital D by 2d. That is about the bright fringe. Next, the condition for dark fringe on the screen. For example, a point P is dark if the path difference is odd multiple of half wavelength. This is the condition we have already derived in previous classes. Then study the interference, a superposition of two waves having same frequency in the first BSc classes. Then you get this equation. The condition for minimum intensity is a path difference is equal to odd multiple of lambda by 2. Then at distances xn is equal to 2n plus 1 by 2 into lambda d by 2d, you get dark fringe. Distance between any two consecutive dark fringes is equal to x2 minus x1. Here also you get lambda d by 2d. In the last case, we have derived the distance between any consecutive bright fringes, that is equal to lambda d by 2d in equation 1. Similarly, in this case, x2 minus x1 is equal to lambda 2 by 2d. That means the distance between any two consecutive bright or dark fringes is the same, and it is known as fringe width or bandwidth. The distance between any two consecutive bright or dark fringes is known as fringe width or bandwidth. It is denoted by the letter beta. Beta is equal to, from equations 1 and 2 we can say that beta is equal to lambda capital D by 2d. From this equation we can say that beta depends upon wavelength of light, distance between the sources and the screen and distance between the two sources. From this equation we can observe that beta is directly proportional to wavelength of monochromatic light used, and beta is directly proportional to capital D, and beta is inversely proportional to distance between the two sources. Therefore, in order to get the fringes clear, in order to observe the fringes clear, we must have good fringe width. Therefore, the distance between the sources and the screen must be large, D must be large in order to get good beta, and the distance between the two sources must be small because beta is inversely proportional to AD. These are the conditions for to get good interference pattern. That is about fringe width. Next. Next topic is what are the conditions for interference. There are so many conditions for getting good interference pattern. According to the conditions, they are divided into three categories. They are condition for sustained interference. The first one is conditions for sustained interference. That means in order to get the fringes continuously, what are the conditions? The next part is condition for good observation. In order to observe the fringes clearly, we have to satisfy some conditions. The third one is condition for good contrast. Good contrast means in interference fringes, some fringes are bright, some fringes are dark. If the bright fringe has maximum intensity and the dark fringe has zero intensity, then both the fringes have good contrast. Bright is perfectly bright and the dark is. For this purpose, there are some other, we must satisfy some other conditions. In this way, according to our situation, we have to derive the conditions for interference. They are divided into three categories. The first one is conditions for sustained interference. In this case, there are two important points. The first and foremost important point is the two sources must be coherent. The two sources must be coherent. In last topic, we have discussed about interference. For the formation of interference, the rays must come from two coherent sources. Therefore, coherence means two sources are said to be coherent. They gives the waves with constant phase difference, then they are said to be coherent. Then any time they must maintain a constant phase difference, then only we get continuous interference pattern. Therefore, the first and important point is to get the interference pattern, sustained interference, the two sources should be coherent. That means they should vibrate in same phase or they should be at a constant phase difference between them. The next one. The second point in this case is the two sources must emit continuous waves of same wavelength and time period. Another condition is we have already told in the interference identical sources, waves from identical sources. Identical means they must emit waves of same wavelength, same time period, same amplitude, etc. Therefore, in order to observe the interference pattern continuously, the two sources must emit continuous waves of same wavelength and time period. These two belongs to the category of condition for sustained interference. When these two conditions are satisfied, then we get a good interference pattern for long time. Next, condition for good observation. In the derivation of fringe width, we get the formula beta is equal to lambda d by 2d. In this case, beta is inversely proportional to 2D. That means as distance between two sources 2D is small, then fringe width is large. That means the distance between two successive fringes is large. If it is very small, they merge each other, we cannot observe bright and dark fringes. In order to observe bright and dark fringes clearly, the separation between the two sources, that means 2D should be small in the above in the formula. Beta is inversely proportional to 2D. As 2D decreases, beta increases. Therefore, 2D should be small to get good fringes. Next point, the distance between sources and the screen should be large. In this formula, beta is directly proportional to capital D. Capital D is the distance between sources and the screen. As D increases, beta also increases. Therefore, distance between the sources and the screen should be capital D should be large. Next, for good observation, the background should be dark. That is the third point. These are the 3 points for good observation. The last case is condition for good contrast. If the intensity of the bright band is small and intensity of the dark band is high, then there is no separation between bright and dark bands. For good contrast, the intensity of the bright band must be high and intensity of the dark band is equal to 0. Then only we can differentiate bright and dark bands. For this purpose, there are some conditions. In the superposition principle, the intensity is maximum when these two waves superimpose each other, then resultant amplitude is equal to A1 plus A2. A1 and A2 are the amplitudes of the two waves. In the previous classes, we have already studied interference of waves. In that class, in that topic, maximum amplitude is maximum. When amplitude is maximum, the resultant amplitude A must be equal to A1 plus A2. If the amplitudes of interfering waves should be equal or nearly equal. This is because for maximum intensity, amplitude must be large. For maximum intensity, according to the conditions, the resultant amplitude A is equal to A1 plus A2. For minimum intensity, A is equal to A1 minus A2. If they are equal, A is equal to A plus A. A1 plus A2, A plus A, that is equal to 2A. Then intensity I is equal to A square, that is equal to 2A whole square, that is equal to 4A square. The minimum amplitude is A1 minus A2. If they are equal, A minus A, that is equal to 0, intensity is also equal to 0. That means intensity of dark band is 0 and the intensity, and that is dark band is perfectly dark and the intensity of bright band is high, it is perfectly bright. Then we can observe the contrast between bright and dark bands. Therefore, in order to get good contrast between bright and dark fringes, the amplitudes of the interfering waves should be equal or nearly equal. Then only the dark band has 0 intensity and bright band has maximum intensity. Then we can differentiate bright and dark bands. Next, the two sources should be narrow. The second condition is the two sources should be narrow. That's why in Young's double slit experiment, the S1 and S2 are two narrow pinholes. So they act as two narrow sources. Next one, the last one is the two sources should be monochromatic sources. In the last slide, beta, we know that beta depends upon lambda. If light has different lambdas, different colored fringes are observed, then fringe width is different. Therefore, in order to get a single colored fringes, if you use white light is a composite light. It consists of different wavelengths and different colored fringes are observed and they are not clear. Therefore, in order to get good contrast between bright and dark fringes, we must use monochromatic source. Monochromatic means so light having single wavelength is known as monochromatic, single colored light. We must use single colored light. In general, in our laboratories, we use sodium light as monochromatic light, but it has two wavelengths very close to each other, but it is taken as monochromatic light having wavelength 5893 angstroms. These are all the conditions for interference. Once again, I repeat this point. These conditions are divided into three broad categories. The first condition is condition for sustained interference. In this case, the two sources must be coherent and the sources must emit continuous waves of same wavelength and time period. Then only we can observe interference pattern for a long time. The second one is condition for good observation. In this case, 2D must be small, capital D must be large, and the background should be dark. Otherwise, the intensity of the light in the background then reflects on the fringe, then we cannot observe interference fringes. Next, for good contrast, the amplitude of the two waves must be equal or nearly equal. The two sources should be narrow, and we must use a monochromatic source of light for the formation of interference fringes. These are all the conditions for interference. The last topic in this lesson is types of interference. Interference is divided into two classes. The first one is division of amplitude wavefront, and next one is division of amplitude. We have already discussed in the phenomenon of interference, the two sources must be coherent. Coherent sources means sources giving waves which are maintaining a constant phase difference are known as coherent sources. Maintenance of constant phase difference is very difficult. Therefore, we cannot produce coherent sources from two individual sources. Therefore, a single source is taken, and the wavefront from the single source is divided into two wavefront. Therefore, it satisfies the condition of waves having same wavelength. They are derived from the same source. Therefore, all waves have same amplitude, same wavelength, time period, etc., and they maintain the constant phase. In this way, in order to produce coherent sources, a single source is taken. The wavefront from the single source is divided into two parts by the phenomenon of reflection or refraction. Then these two parts of same wavefront travel unequal distances and reunite at some point, and they produce interference bands. This type of interference is known as division of wavefront. Mainly, in order to produce two coherent sources, a single wavefront is divided into two parts. For this purpose, different apparatus are used. Fresnel used a biprism to divide a single wavefront into two wavefronts, and by the method of refraction. And Lloyd used a mirror in which the reflection takes place, and a single wavefront is divided into two wavefronts. In this way, different instruments are used. They are, for example, Fresnel's biprism, Lloyd's mirror are used for the division of wavefront. Therefore, Fresnel's biprism experiment and Lloyd's mirror belongs to this class, that is division of wavefront. In these instruments, interference is formed by the division of wavefront. That is about division of interference by division of wavefront. Next one is division of amplitude, interference by division of amplitude. In this case, a single ray beam is divided into two parts, either by parallel reflection or refraction. This is the second case. This case is used in Newton's rings arrangement, and Lloyd wedge film, Michelson's interferometer, all thin films. On all thin films, a single beam of light is allowed to incident on that thin film, and it is reflected at the upper and lower parts of the film. A single beam is divided into two beams having equal amplitudes. Then all the conditions for interference are satisfied. The two reflected rays act as two sources. Then they reunite and interference pattern is formed. This is a division of amplitude in all thin films, which are used in wedge film, Newton's rings, Michelson's interferometer. In all these experiments, the interference belongs to division of amplitude. In this way, interference is divided into two categories: division of wavelength and division of amplitude. The main purpose is to produce coherent sources. For this purpose, different devices, different arrangements are used in different experiments, but the final purpose is to get interference fringes by producing two virtual coherent sources. That is about types of interference. That is about interference and conditions for bright and dark bands. What are different conditions for observing interference bands or interference fringes, and what are the different types of interferences for producing coherent sources in different experiments. These are all about interference and types of interference, etc. Thank you.